Here's a new example. I want to solve this separable differential equation. My first step is to try to get the x's on one side and the y's on the other. So I'll multiply both sides of this equation by dx, with dy equals e to the x minus y times dx. This might seem difficult to separate the x from the y here, but remember this rule that you learned in Algebra 2 probably, maybe Algebra 1. If you had x to the 10th over x to the 4th, the result would be x to the 10 minus 4, x to the 6th. Well, this rule works backwards too, and that's what we're going to learn. That's what we're going to use here. So e to the x minus y is the same as e to the x over e to the y. That works because those two powers have the same base. So e to the x and e to the y have the same base, e. So I can write that expression as e to the top exponent minus bottom, e to the x minus y. So it means it's legal for me to go backwards and write e to the x minus y as e to the x over e to the y. So there's my new equation. My next step, I'm going to multiply both sides of this equation by e to the y. Once I do that, now my variables are separated. I have e to the y times dy is equal to e to the x times dx. Remember the next step, I'm going to integrate both sides. So you're going to see me put an integral sign on both sides of that equation. Now I'm going to integrate e to the y with respect to y on the left-hand side, and integrate e to the x with respect to x on the left-hand side. So good news is, that's our favorite integral. So e to the y is equal to e to the x. Remember, the plus a constant has to go on one side. Typically, by conventionally we put it on the right-hand side. So e to the y is equal to e to the x plus c. The next step, I think it's easiest in this case, to find c next. So that's going to be my next step, is to find the c. So I'm going to take a tiny break from that flow I had going. I'm going to take the equation I have, e to the y is equal to e to the x plus a constant. I'm going to replace y with 2 and x with 0 because those are my initial condition. So I get e squared is equal to e to the 0 plus a constant. Well, e to the 0 is simply 1. So my new equation, e squared is equal to 1 plus c. I'm going to try to isolate the c, so I'm just going to subtract 1 from both sides, and I get that c is equal to e squared minus 1. Now that I've found c, I'm going to pick back up where I left off. I had e to the y is equal to e to the x plus c, but now I know what c is. I know c is equal to e squared minus 1. So I'm going to replace the c with e squared minus 1. My next step, my last step actually, I'm trying to get y by itself. So what's happening to y on the left-hand side? Well, y is the exponent on a base of e. So to undo an exponent on a base of e, we're going to take the natural logarithm of both sides. So that gives me the natural log of e to the y is equal to the natural log of the other side, e to the x plus e squared minus 1. Well, natural log of e to the y, remember that natural log and e to the are inverse operations, so they're going to undo each other and leave behind y. So my final answer on the left-hand side, y, and on the right-hand side is equal to the natural log of e to the x plus e squared minus 1. I made a suggestion to you before that when you finish a separable differential equation problem, you at least take a minute and stop and check to see that your initial condition still holds. So we'll check that. 2 is equal to the natural log of e to the, we're going to use 0 for x, plus e squared minus 1. So 2 is equal to the natural log of, well, e to the 0 is 1, plus e squared minus 1. Is 2 equal to the natural log of e squared? Yes, it is. That's true.